The output displays the grid and the shortest path from S to G around the obstacles. The path length counts the steps from start to goal. You've implemented a pathfinding on a 2D grid, complete with a priority queue, custom heuristics, and path reconstruction. This algorithm is at the heart of game AI, robotics, and any application that needs to navigate around obstacles efficiently. The demo creates a 10 by 10 grid, places a wall of obstacles, and runs a with diagonal movement allowed. It then builds a character display showing the start, S, goal, G, obstacles, hashtag, and the path. The path length is printed to the console. These methods collect up to 8 neighboring cells. Add if valid ensures we don't go out of bounds. The diagonal neighbors are only added when allow diagonal is true. Is walkable checks bounds and the walkable array. Cost returns 10 for orthogonal moves, and 14 for diagonal if allowed, approximating SQRT, 2, is almost equal to 1.4. The heuristic uses the octal distance when diagonals are allowed, otherwise the Manhattan distance. These are standard admissible heuristics that guarantee optimal paths. Starting from the goal node, we follow parent references back to the start. The resulting list is reversed so it reads from start to goal. This gives the complete sequence of steps. The loop pulls the node with the lowest F cost from the open set. If it's the goal, we reconstruct the path. Otherwise, we mark it as closed and examine its neighbors. For each walkable neighbor not yet closed, we calculate a tentative G cost via the current node. If the neighbor is new or we found a cheaper path, we update its costs and parent, then add or reinsert it into the open set. Reinsertion is necessary because the priority queue doesn't automatically reorder when an element's cost C. The main method begins by rejecting the search if either start or goal is blocked. It creates a priority queue open set for nodes to explore and a closed set for already processed nodes. The start node's costs are initialized, G cost is 0, we're already there, and H cost is the heuristic distance to the goal. The start node is added to the open set. The main class stores the grid dimensions, a 2D Boolean array indicating walkable cells, and a flag for diagonal movement. The constructor initializes these fields. The grid size is derived directly from the input array. We start with a node class representing a grid cell. It stores coordinates, the cost from the start, G cost, the heuristic estimate to the goal, H cost, and a reference to the parent node for reconstructing the path. F cost returns the sum of G cost and H cost, which it uses to decide which node to explore next. The compare to method orders nodes by their F cost, breaking ties with the heuristic. Proper equals and hash code allow nodes to be stored in hash-based collections. We're implementing the A pathfinding algorithm, the same technique used in games and robotics to find the shortest route around obstacles. This single Java file includes a priority queue, heuristic functions, and path reconstruction. Let's walk through every piece.